In September 2023, deep beneath the drifting sands near Wuwei, in China's Gansu province, engineers at the Shanghai Institute of Applied Physics pushed a control rod fraction by fraction from a reactor core no bigger than a shipping container. The needles on their monitors crept upward. Then, criticality. A self-sustaining nuclear chain reaction achieved inside the TMSR LF1, the Thorium molten-salt reactor, liquid fuel, Unit 1. 2 megawatts of thermal output, barely enough to power a few thousand homes, yet the number mattered less than the machine itself. For nearly 5 decades, no molten-salt reactor anywhere on Earth had run. The last one went dark in Tennessee in 1969. Now, in a facility ringed by desert scrub and concrete blast walls, a design once abandoned by the country that invented it was breathing again, this time in China. The location was no accident. Gansu's remoteness offered isolation for an experimental design still unproven at scale. Instrumentation bunkers, radiation monitors, and redundant containment structures surround the site, built to contain a reactor unlike almost anything operating commercially today. Inside, instead of solid fuel rods, a fluoride salt mixture laced with fissile material circulates as a liquid, carrying heat and radioactive byproducts through pipes engineered to survive extreme chemical stress. State media called it a milestone in China's push toward energy independence. Western nuclear engineers called it something else, a resurrection. The technology traces its bloodline directly to a Cold War-era American laboratory, where scientists first proved molten salt could sustain fission, then watched Washington shelve the entire concept in favor of other reactor designs. 60 years separate that laboratory from this desert. 60 years in which molten salt technology sat dormant in filing cabinets and technical reports, waiting for a nation willing to spend the money and time to rebuild it from scratch. Why did the design that once ran successfully in Tennessee disappear for 2 generations, only to resurface now in the Gobi? The answer begins not in China, but in a research lab in Oak Ridge, Tennessee, where the entire concept was born, tested, and ultimately buried. In 1965, inside a squat concrete building at Oak Ridge National Laboratory in Tennessee, American scientists switched on a reactor unlike anything the nuclear industry had built before. The molten salt reactor experiment, MSRE, contained no fuel rods, no water coolant, no towering pressure vessel. Instead, a mixture of lithium and beryllium fluoride salts, laced with dissolved uranium, flowed through graphite channels at temperatures near 650 degrees Celsius, glowing faintly orange as it carried heat away from the core. Visitors described the pipes as warm to the touch, even through insulation, a detail then unheard of in reactor design. For 4 years, the reactor ran almost continuously. Engineers logged more than 13,000 hours of operation, cycling through uranium-235 fuel, then uranium-233 bred from thorium, proving that a liquid fuel design could sustain fission reliably, refuel without shutdown, and survive the corrosive chemistry of molten fluoride salts using a nickel alloy called Hastelloy N, developed specifically for this program. Alvin Weinberg, the laboratory's director, believed molten salt technology represented nuclear power's safest, most efficient future. He pushed for a follow-up, a 250-megawatt thorium breeder reactor that could have proven the concept at commercial scale. Congress never funded it. By 1969, political winds had shifted. The Nixon administration consolidated federal reactor research behind a single technology, the liquid metal fast breeder reactor, a solid-fuel plutonium design favored by weapons-adjacent research and a nuclear establishment already invested in conventional fuel fabrication infrastructure. Weinberg lost his directorship in 1973 after continuing to argue publicly for molten salt. Funding for the entire program ended. The MSRE was drained, decommissioned, and left to decay in place. Its technical reports, thousands of pages documenting corrosion rates, chemical processing methods, and operational data, sat largely unread in American archives for decades. 54 years passed. No nation built another molten salt reactor. Then Chinese researchers, working from declassified Oak Ridge documents, began asking a question American policymakers had abandoned. What if thorium, not uranium, became the foundation of nuclear power's next chapter? The answer required understanding an element that occurs almost nowhere on Earth in a form ready to fission on its own. Thorium sits quietly in Earth's crust, roughly 3 to 4 times more abundant than uranium-235, the isotope that fuels nearly every commercial reactor operating today. Geologists have mapped thorium deposits across India, Australia, Norway, Brazil, and the United States. But China's reserves concentrate heavily in one place. Bayan Obo, in Inner Mongolia, an enormous mining complex originally developed for rare earth extraction. Estimates place recoverable thorium there near 100,000 tons, a byproduct sitting in tailings alongside neodymium and other rare earth ores already mined for magnets and electronics. That abundance alone explains part of thorium's appeal. Uranium-235 makes up only 0.7% of natural uranium, requiring energy-intensive enrichment facilities to concentrate it into usable reactor fuel. Thorium-232, by contrast, exists almost entirely as a single isotope, eliminating the enrichment step altogether. For a country like China, sitting on thorium-rich mining waste with no established use, the element looked less like a rare resource and more like a stockpile waiting for a reactor design that could burn it. But thorium carries a critical limitation. It cannot sustain fission by itself. Natural thorium-232 is fertile, not fissile. Dropped into a reactor alone, it does nothing. To become useful fuel, a thorium-232 nucleus must first absorb a stray neutron, transforming into thorium-233, then decaying through protactinium-233 over roughly 27 days into uranium-233, the actual fissile material capable of sustaining a chain reaction. This means every thorium reactor needs a neutron source and an initial fissile driver fuel, typically enriched uranium or plutonium, to start the process and keep converting thorium into usable material. Once running, a well-designed reactor can breed uranium-233 continuously from the thorium blanket surrounding or dissolved within its core, extending fuel supplies far beyond what the driver fuel alone could sustain. China's engineers built the TMSR LF1 specifically to test this transformation in practice. A working demonstration of thorium's slow conversion into fissile material inside a functioning reactor core, not just a laboratory calculation. The next question was how to keep that fuel. Now radioactive, chemically hostile, constantly transforming. Physically present inside the reactor without ever encasing it in a solid rod at all. Inside the TMSR LF1's core, there are no fuel rods, no zirconium cladding, no solid pellets stacked in bundles. Instead, the fuel itself is a liquid, a mixture of lithium and beryllium fluoride salts, technicians call it F-Lib, with uranium-233 dissolved directly into the molten mixture, circulating at roughly 650 degrees Celsius through a closed loop of piping and heat exchangers. This single design choice changes almost everything about how the reactor behaves. In a conventional reactor, Fuel sits fixed in place for months or years, sealed inside metal tubes that must be physically removed, cooled, and stored once spent. In the Gansu reactor, the fuel moves continuously, pumped through the core where fission occurs, then out into external loops where heat transfers to a secondary system, then back again, cycling roughly once every few seconds. Because the fuel flows as liquid, operators gain a capability solid fuel reactors simply cannot offer. They can add fresh fissile material or remove problematic fission products without ever powering down the reactor. Xenon-135 and other neutron-absorbing fission products, which in conventional reactors gradually poison the fuel rods until refueling becomes necessary, can instead be stripped continuously from the circulating salt through a side process, keeping the core's reactivity stable for far longer stretches between major interventions. This continuous processing capability directly targets one of nuclear power's oldest bottlenecks, the refueling outage. Pressurized water reactors typically shut down every 12 to 18 months, idle for weeks, while technicians swap fuel assemblies manually inside radiation-shielded pools. A molten-salt reactor, in theory, could run for years without that same interruption, chemically adjusting its fuel composition on the fly rather than replacing physical components. But moving radioactive, corrosive, superheated liquid through pipes and pumps introduces its own set of engineering demands, unlike anything found in a conventional plant. Every valve, weld, and heat exchanger surface sits in direct, continuous contact with molten fluoride salt carrying intensely radioactive material at temperatures hot enough to soften ordinary steel. Keeping that fluid contained without leaks, without pressure buildup, without corrosion eating through the walls would define the entire engineering challenge that followed. And the very absence of pressure that made this possible also came with a hidden mechanical price. Conventional nuclear power runs on a brute force compromise. Water makes an excellent coolant and moderator, but at normal atmospheric pressure, it boils at just 100 degrees Celsius, far too low to extract useful thermal energy for electricity generation. Engineers solved this by crushing the water under enormous pressure. France's fleet of 58 pressurized water reactors operates coolant loops at roughly 155 atmospheres, pressure found more than a mile beneath the ocean's surface, forcing water to remain liquid above 300 degrees Celsius. That pressure demands enormous engineering overhead. Reactor vessels must be forged from steel walls, often exceeding 20 centimeters thick, capable of containing a catastrophic failure without rupturing. Pipes, valves, and pumps throughout the primary loop require pressure ratings far beyond what any other industrial process typically demands. A pressurized water reactor's containment building, that familiar concrete dome recognized around the world, exists largely to survive the consequences if that pressurized water loop ever fails catastrophically, flashing instantly into steam. Molten salt eliminates this problem entirely, not by containing pressure more effectively, but by removing the need for it. Fluoride salt mixtures like the F-Lib compound used in the TMSR LF1 remain liquid at ordinary atmospheric pressure across an enormous temperature range, staying fluid well past 700 degrees Celsius without any need for pressurization at all. The reactor's operating temperature near 650 degrees Celsius sits comfortably within that liquid range, achieved without a single atmosphere of excess pressure applied. This single difference reshapes the entire mechanical philosophy of the reactor. Vessel walls at Wuwei carry a fraction of the mechanical stress found in a pressurized water reactor's primary loop, since there's no driving force pushing to rupture the container beyond its intended shape. Thinner walls, lighter piping, and simplified containment structures become possible, translating into potentially lower construction costs and reduced risk of the sudden, explosive depressurization events that have driven safety design in conventional nuclear plants for 70 years. But building a reactor with drastically reduced pressure risk doesn't eliminate risk altogether. It shifts it elsewhere into different failure modes entirely. What happens if cooling systems fail, pumps stop, and that superheated radioactive salt has nowhere to safely go? The answer sits beneath the reactor core itself, in a component with no moving parts at all. Beneath the core of the TMSR LF1, hidden in the reactor's lower plumbing, sits a small section of pipe no wider than a fist. Inside it, a plug of frozen fluoride salt blocks the path to a set of dump tanks buried further underground. That plug stays solid for one reason only. A small electric fan blows continuously across the pipe, holding the temperature just below the salt's freezing point of roughly 450 degrees Celsius. It is a strange kind of safety system because it depends on staying cold rather than staying powered up in the usual sense. Cut the electricity and the fan stops. Without airflow, residual heat from the reactor itself creeps into the plug within minutes, and the frozen salt begins to soften. Once it liquefies completely, gravity does the rest. The entire radioactive fuel load, still dissolved in its carrier salt, drains downward through the open channel into passively cooled tanks designed to spread the material thin and shed heat on their own, with no pumps, no valves, and no operator required to throw a switch. Engineers at the Shanghai Institute of Applied Physics call this a walk-away safe design, and it stands in sharp contrast to the elaborate emergency cooling systems required in pressurized water reactors, where active pumps must keep circulating water even after shutdown to prevent meltdown. Fukushima's 2011 crisis unfolded precisely because those pumps lost power. The freeze-plug removes that dependency entirely. The failure mode is not an accident to be prevented. It is the shutdown mechanism itself. Oak Ridge's original molten-salt reactor experiment used the same trick in the 1960s, draining its fuel into tanks every night during shutdown tests, over and over, without incident. China's engineers have now rebuilt that concept with modern sensors monitoring plug temperature in real time, feeding data back to control rooms above ground in the Gansu Desert. But passive drainage solves only the danger of losing control over heat and radiation. It does nothing to address a separate, quieter problem lurking inside every molten salt design. What happens, chemically and physically, to the waste products still dissolved in that salt long after the reaction stops, and how much of that waste the world could actually learn to live with. Spent fuel from a conventional uranium reactor remains dangerous for extraordinarily long stretches of time, largely because the process creates plutonium-239, an isotope with a half-life of 24,100 years that dominates long-term storage calculations at sites like Yucca Mountain in Nevada. Thorium fuel cycles take a different chemical path. When thorium-232 absorbs a neutron, it transmutes into uranium-233 through a short-lived chain involving protactinium-233, and this route rarely produces the heavy transuranic isotopes that make conventional spent fuels so persistent. Fewer neutron captures happen at the higher end of the periodic table, so less plutonium, americium, and curium accumulate in the waste stream to begin with. Researchers at the Shanghai Institute of Applied Physics have modeled the resulting waste profile from the TMSR LF1 and published projections suggesting that residual radioactivity could decay to levels considered safe within roughly 300 years, compared to the tens of thousands of years required for uranium-plutonium spent fuel from reactors like those at France's Graveline's plant. 3 centuries is still a long institutional commitment, longer than the United States has existed as a nation, but it collapses the storage problem from a geological timescale to something resembling a multi-generational engineering project. There is a second advantage tied directly to the liquid fuel itself. Because fission products stay dissolved in the flowing salt rather than trapped in solid rods, operators can theoretically extract specific isotopes continuously, pulling out xenon and krypton gases that would otherwise poison the reaction and separately isolating dangerous long-lived species for concentrated storage, rather than leaving everything mixed together in bulky spent fuel assemblies. Oak Ridge's original experiment demonstrated primitive versions of this gas-stripping process back in the late 1960s using helium bubbling. But smaller waste volumes and shorter half-lives on paper mean little until engineers can actually build a chemical plant capable of separating uranium-233 from a searingly hot, intensely radioactive salt mixture without destroying the equipment doing the separating. And that engineering challenge exposes one of the ugliest secrets of molten salt technology. The very chemistry that makes this fuel cycle appealing is also what has been quietly corroding reactor components since the 1960s. Fluoride salt at 650 degrees Celsius does not behave like a passive liquid sitting in a pipe. It behaves like a slow chemical acid, and at Oak Ridge National Laboratory between 1965 and 1969, that chemistry nearly ended the molten salt concept before it could mature. Engineers there used a nickel-based alloy called Hastelloy N to build the reactor's piping, betting it could withstand fluoride exposure over the long term. Instead, fission product tellurium, generated continuously inside the circulating fuel, worked into microscopic grain boundaries in the metal and caused a specific failure mode researchers named tellurium cracking. Pipe walls thinned, welds became brittle, and components that should have lasted decades needed replacement within a handful of years. The Oak Ridge team compensated by swapping sections during scheduled shutdowns, treating corrosion as a maintenance routine rather than a solved problem. And when funding disappeared in 1969 under Nixon-era energy priorities favoring solid-fuel plutonium breeders, the corrosion question went unanswered for 54 years. China's engineers inherited that unfinished chemistry problem directly. At the Shanghai Institute of Applied Physics, metallurgists have developed modified nickel alloys with adjusted chromium and molybdenum content, aiming to resist tellurium infiltration better than the original Hastelloy N formulation. The TMSR LF1 also carries online chemical monitoring equipment that samples the salt continuously, tracking oxidation states and impurity levels in real time, so operators can adjust conditions before corrosion accelerates, a capability Oak Ridge's team never had access to in the 1960s. Early results from the Gansu site reportedly show improved alloy performance, though the reactor has so far logged only a fraction of the 13,000 operating hours Oak Ridge eventually accumulated. No molten salt reactor anywhere in the world has yet run continuously for decades without major material replacement, and until one does, corrosion remains an open engineering question rather than a solved one. That unresolved chemistry sits at the center of a much larger obstacle still ahead. Even a corrosion-resistant reactor produces spent fuel that must eventually be chemically reprocessed, separating usable uranium-233 from lethal fission products. And that separation step has barely been attempted outside a laboratory beaker. Reprocessing molten fuel is not a matter of pouring liquid through a filter. Uranium-233 must be chemically separated from a mixture containing dozens of intensely radioactive fission products, some emitting gamma radiation strong enough to require thick lead and concrete shielding around any equipment that touches the salt. Oak Ridge experimented with fluoride volatility separation in the late 1960s, extracting small test quantities under laboratory conditions, but never built anything resembling an industrial-scale plant before the program's cancellation. China's engineers at the Shanghai Institute of Applied Physics have only just begun similar work, currently testing separation chemistry at gram-scale quantities inside shielded hot cells, a tiny fraction of what a working power plant would eventually process on a daily basis. Scaling that chemistry from grams to kilograms and eventually to tons means building remote-handling robotics, corrosion-resistant vessels for the separation process itself, and waste conditioning lines to package leftover fission products for storage, none of which currently exist outside limited prototypes. The reactor engineering and the fuel cycle chemistry must advance together, and neither is finished. Officials at Wuwei have outlined a deliberately incremental roadmap. After the 2-megawatt TMSR LF1 completes its test campaign, the next step is a 10-megawatt successor reactor, 5 times larger, intended to validate longer continuous operation, alloy durability under sustained neutron flux, and larger-scale reprocessing before anyone attempts a commercial unit. Only after that intermediate reactor proves itself will engineers consider designs exceeding 100 megawatts, the threshold generally considered necessary for feeding electricity into a national grid at meaningful volume. No public timeline commits to a specific year for that commercial reactor, a silence that speaks to how many unresolved variables remain in alloy performance, reprocessing throughput, and long-term operational data. What China has proven, decisively, is that a thorium molten-salt reactor can be built and brought to criticality in the 21st century using modern materials and monitoring, resurrecting a design the United States abandoned in 1969. What remains unproven is whether that design can survive continuous industrial operation for decades, process its own fuel economically, and scale to sizes that matter for global energy production. The Gobi Desert facility exists to answer those questions one measured step at a time. This experimental reactor tests tomorrow's nuclear fuel today.